Okay, we'll start with the bicycle problem. 30 feet in the air, 30 feet on a hill, and we roll down the hill, get the velocity at the bottom, pretty steep hill. The velocity at the bottom is what we're trying to find. Set the kinetic energy at the bottom equal to the potential energy at the top. And we have 1/2 mv squared equals mgh. You can cancel the m from both sides and come to the conclusion that v is equal to the square root of 2gh. So v equals the square root of 2 times 32.2 feet per second squared times h, which was 30 feet. That comes out to about 44 feet per second, which probably most of you had, but I didn't have the units in there. So that's my mistake, and I will tighten you up for that, and you'll get points for whatever you put there. I left the units off, and you should know that in every engineering problem there should be some units as part of the answer. So what I intended for you to do was convert that to miles per hour by multiplying 3,600 seconds per hour and dividing by 5280 feet per mile. Accordingly, the units will cancel in rearranging. The feet cancel the feet, the seconds cancel the seconds, and we wind up with the velocity at the bottom was equal to 30 miles per hour, approximately 30 miles per hour. Okay, moving on to problem 2, we have a lake. We're pumping still water out of the lake, raising it up to the top of a spray tower. Here's our spray tower. 30 feet high, and spraying it into the top of this tower. The velocity at the top is 20 feet per second, and the height that we've raised it is 30 feet. So we have the power that we've added. We have a pump down here doing this, and the power that we've added to this pump, let's call that W dot into the pump. W dot is work per time is equal to, well, let's see, how do we raise the energy of the fluid? There's kinetic energy. We'll put the m outside, 1/2 v squared plus g times h for the potential energy. And that's the total work, let's say, to move this mass from the bottom to the top and have it at this high velocity. But we want mass per time, a mass flow rate, so we'll put a dot over that, and this will make the units consistent. The work to move the mass up would be mv squared plus mgh. The work per time would be a flow of mass, and you have a flow of work, which is horsepower. So we take our units and put them in. We have, let's see, 3 horsepower. Now I'm going to convert that times 550 foot-pound force. And those of you in mechanical engineering will get to use foot-pound force quite a lot. 550 foot-pound force per second is equal to 1 horsepower. So that's per horsepower. Is equal to m dot times, and I'll put 1/2 v squared, which is 20 squared, plus G times H, 32.2 times 30, and all that'll be feet squared per second squared. Now I'm going to multiply this right-hand side times 1 pound force per 32.2 pound mass feet per second squared. All that's multiplying the right-hand side. Now we'll check our units. If we cancel out the pound force on either side, and we cancel out, let's see, the second squared with this second squared, the m dot will have units of pound mass per second. Well, we'll just find what's left when we solve for m dot. We have this squared will cancel the foot here, and this foot will cancel the other foot. Our horsepower cancels out. And when we solve for m dot will have units of pound mass per second. So what we wind up with is m dot. When we solve this equation, m dot is equal to 45 pound mass per second. So that should take care of problem 2. That was kind of a difficult problem, probably the most difficult one in this quiz. Finally, our last problem, we have a duct 3 feet in diameter, 20 pounds per second going in it, pound mass per second. It's the mass flow, and it's air. The pressure is 10 psig. We have to add the atmospheric pressure into it, so we'll assume that's about 14.7 psi, and we have 24.7 is our pressure, psia. Our temperature of the air is 80 degrees Fahrenheit. We have to get that into absolute units, so add 460, and that'll come out to 540 degrees Rankine. Our cross-sectional area is equal to pi d squared over 4, so that's 3 squared over 4 feet squared. And then we're going to use the ideal gas equation. P V equals m dot over molecular weight RT. Equals m dot, so we have V dot, the volume flow, and the mass flow. What we're doing is just taking our mass and taking it per time. That'll be proportional to the volume per time. But of course, V dot, the volume flow, is the area times the velocity, and we'll call that U. Solving for U, we have U is equal to m dot RT over P times pi d squared over 4. There's our area. Times, and also divided by the molecular weight. Plugging in the numbers, we have 20 pound mass per second times 10.73. That's the R that we're going to use. That's psi feet cubed per pound mole degree Rankine times 540 degrees Rankine, all of that divided by 24.7 psi times pi times 3 squared over 4 feet squared times the molecular weight, which for air is approximately 29 pound mass per pound mole. When we're all done, we find U is equal to approximately 22.9, scratch that, 22.9 or approximately 23 feet per second. And that solves problem 3.